Welcome to our journey through gravity's history. This title slide pairs an apple, orbital diagrams, and data charts to hint at experiments and equations ahead. Over the next slides, we'll follow how simple observations and precise measurements transformed a mystery into quantitative science, linking falling apples to orbiting planets and the modern instruments that test gravity. Galileo marked a shift to measurable science by timing falling bodies, defining inertia, and turning motion into mathematics. The sketches summarize his time-squared law, the idea that objects stay in motion unless acted upon, and the early mathematization of trajectories, setting up the experimental and conceptual groundwork that Newton would later synthesize. Newton unified earthly and celestial mechanics with a single formula, F equals gm1m2 over r squared, explaining why apples fall and planets trace ellipses. The diagrams emphasize Inverse's square weakening, tidal pulls, and predictable cometary paths, showing how a quantitative gravitational law connected Kepler's observations, tides, and trajectories under one framework. The Cavendish experiment introduced the torsion balance to measure the tiny gravitational attraction between masses and, crucially, to quantify the gravitational constant g and infer Earth's density. The illustration of suspended masses and a mirrored scale highlights how painstaking laboratory precision converted celestial proportionalities into concrete numbers, giving Newton's law experimental anchoring. By the 19th century, several puzzles challenged the existing picture. Newton's instantaneous action conflicted with the finite speed of light, Mercury's perihelion showed an unexplained advance, and field-based ideas began to replace action of distance. The slide's conflict diagrams and anomalous orbit show why scientists sought new frameworks compatible with electromagnetism and finite propagation speeds. Einstein's journey from 1905 to 1915 began with special relativity and the realization that the speed of light is an absolute limit, a constraint incompatible with Newton's instant gravity. A decade of intense theoretical struggle followed, culminating in 1915's general relativity, where gravity became the curvature of space-time rather than a traditional force. Eddington's 1919 eclipse expedition measured starlight bending around the sun and found results matching Einstein's prediction instead of Newton's, illustrated here by divergent light paths and observational instruments. This empirical confirmation replaced Newtonian attraction with space-time geometry and rapidly propelled general relativity from theory into worldwide scientific prominence. High-precision experiments have repeatedly validated space-time curvature. Observed frequency shifts demonstrate gravitational redshift. Radar delays reveal the Shapiro time delay. GPS systems require relativistic corrections for everyday accuracy, and lensing maps chart mass and dark matter. The icons and sketches on this slide show how relativity underpins both precise measurements and modern technologies. Einstein derived wave solutions in 1918, but early work raised skepticism about their physical reality and coordinate artifacts. Mid-century breakthroughs by Bondi and Pirani established that gravitational waves carry energy, and subsequent observations confirm them, turning theoretical ripples into an empirical foundation for gravitational wave astronomy. The hunt for gravitational waves evolved from resonant bars in the 1960 seconds to large-scale laser interferometers like LIGO, with sensitivity milestones shown on the timeline. LIGO's first direct detection in 2015 and the 2017 multi-messenger observation of a neutron star merger, seen in both gravitational waves and light, inaugurated a new era of astrophysical discovery. Gravitational waves occupy a wide spectrum from nanohertz pulsar timing arrays to millihertz space missions like LISA, illustrated across the frequency diagram. Different bands probe supermassive black hole growth, early universe phase transitions, and fundamental physics, enabling multi-frequency astronomy that traces cosmic history from the largest scales to primordial moments. Open frontiers in gravitational physics include bridging quantum mechanics and general relativity at the smallest scales, searching for geometric signatures of dark energy, testing gravity's stronger field behavior near supermassive black holes, and pursuing a single unifying theory. The slide's icons capture these active research directions and the ongoing quest to deepen our understanding of gravity